Thank you for the nice introduction, John. And also, first of all, thanks to the members of the assessment committee for taking the time to both assess my thesis, but also traveling here today. I really look forward to discussing my work with you. Also, thank you to everyone that came here to see my presentation, both physically and also those of you participating online. It means a lot that so many have come to see my work. I will now present the work that I've been doing in my PhD under the title Experimental Characterization and New Simulation Methods for Static Failure in Preform Transitions. As a bit of background, my work is not standing alone. It is also part of a larger project called Made Blades, where the overall objective is a 30% cost reduction of produced blades in wind turbines. And this is done in collaboration with industrial partners Wind Power and AG Inventec, and also supported by DTU. It has been financially supported by EUDP. There's also a lot of people that I would acknowledge their participation in my project. First of all, my supervisors, Asbjørn Lindgaard, Brian Bach, I would like to thank for their supervision of me, good guidance. I would also like to thank my colleagues here at the university, my office mates, Christian, Peter, and Sebastian, and also close colleagues, Eglund, Johnny Jacobsen, and Jørgen Kepler. Outside of our university, I would also like from LM Wind Power thank our project managers, Christian Lehmann and Daniel Kirkegaard, for their supervision of the entire Made Blades project. Outside of the Made Blades project, there are two people, Frans van der Meer and Yuri Rocha from TU Delft, who hosted me on my external research day and supported me in the work that I did in the 6 months that I was in the Netherlands. With that, we'll get into the actual presentation. I will start by a small introduction of laminated composites and preform transitions that we're going to discuss more in depth. I will also shortly outline the objectives that preceded the papers that have been written. I'll then discuss the content of the papers and finally conclude on all the work and the impact on industry. Composite structures are typically what we define as lightweight and high performance structures. Examples include race cars, aeroplanes, bicycles, and of course, wind turbines. And the reason that we like composite materials is that they provide some beneficial properties such as good stiffness to weight, good strength to weight, and material tailoring, where we can design the material itself such that it provides the best possible material properties for a given load case. If we stay a little bit with our wind turbine, it is of course the blades that we're looking at. And if we take a cross section here to see how this blade is made, it is consisting of a lot of components. But what we're interested in today is the skins or the outermost layers of this cross section, because this is where we find the laminated composites we're going to study. So a laminate is a stack of material, and if we just take a look at one of these layers, in the pertinent material, glass fiber reinforced polymer, this will consist of a matrix material, namely a polymer such as a polyester or epoxy, which is then reinforced by fibers, glass of course in this case, which are long fibers. And when we manufacture these materials, instead of working directly with individual fibers, they are typically delivered from manufacturers in fabrics. Here we're working with non-crimp fabrics where fibers are always straight as opposed to woven fabrics. And specifically, we have two types that are included in the blades. So we work with unidirectional materials where we have most of all our fibers arranged in one direction, stitched to a small amount of backing fibers here. And then we also have biaxial fabrics where we have two fiber directions stitched to each other. When we want to actually manufacture some structure from these materials in the conventional way, we start with a layer by layer construction. So we have a mold and we have a number of fabrics. We place these fabrics into the mold one by one, and thus we build up our laminate. This is then infused by our matrix material, and after curing, we have a composite laminated structure. This is done manually and requires significant manual labor because we can only handle one fabric at a time, which must be put into the mold. And this is, of course, also time consuming. To approach these problems, this is where the preform concept is introduced. So in the preform concept, we still take the individual layers, but now we build up a preform on a separate preform tray. Part of the project has been to make this automatically. I will just show a video of some of the results that has been obtained, where a robot has been, or a tool has been developed to roll out and lay up automatically. After this, we consolidate the preform, which means that a binder material in between the fabrics is activated such that all the layers are adhered together, so we can manipulate this preform as a single unit. This is then lifted by a crane into our manufacturing mold. All of this is done to reduce the labor intensity, but also, since we're working in the root end of a blade where we have several hundred layers of material, this also means that we can put several tons of glass into the mold at once, which also reduces the production time since we can put all of the glass in the mold faster. When we use preforms, a consequence is that when we have multiple, we will have interfaces created where preforms meet each other. We're going to be working with two preform transition types. One is what we call the transverse preform transition, where fibers are aligned along this interface where the preforms meet. And the other is axial preform transition, where the fibers meet in the interface and are interrupted by this interface as well. Given that we have these interfaces, we must face the fact that interfaces in laminated composites are very often weak spots and initiators of failure. This is what we want to avoid. So we have now a goal that we must maintain structural integrity of our blades. And this is very important when we introduce preforms, because we have a lot of benefits coming from the manufacturing side, but these must not come at the cost of introducing structural weakness in our blades. What complicates our goal a little bit is that large-scale fracture, as shown here, is driven by small-scale damage mechanism, as shown here. And these small-scale damage mechanisms work at the scale of a laminate. So where a blade has been, or are very large by today's standards, over 100 meters, the damages we must actually look at are very small compared to less than a centimeter often. What's more is that damage can interact with each other. So two cracks in close proximity can often grow faster than just one crack alone, even under the same load conditions. But this leads us to the project objectives. So in order for us to avoid failure, we must be able to understand how it happens, and we must be able to predict it. And the topics are then, we must be able to characterize our preform transition, characterize the failures that we see. To do so, we must first of all be able to detect the damages that happen in it. And finally, to avoid structural failure, we must also be able to predict and thus simulate what happens in a preform transition. And these are also the topics covered in the papers A, B, and C. So, getting into the first paper A. Where we have developed a detection method for matrix cracks under the name matrix cracks. The motivation here is that it was discovered, observed that matrix cracking in preform transitions is a significant part of the failure. Characterization involves many cracks, so there are a lot of cracks to keep track of. And for a human operator, detecting each crack individually is both a tedious job and also prone to error. As a short overview of what we do instead, we work with a tension setup shown here. We then take images of our specimens, pass them through our method, and the output is that from a raw image, we can detect cracks with good accuracy. The conditions for loading is quasi-static loading under constant load rates. And the way that we obtain our images is what's called transilluminated white light imaging, where we have a light source placed behind our specimen, and then we capture the light that is transmitted through our specimen. And what this does is that it allows us to visualize subsurface damage, specifically matrix cracks that are happening in the middle of our laminate. What's also nice in this method is that it has a simple setup. We only need a light source, constant light source, and a camera. There's no need for exotic or expensive equipment in our experiments. When we do the experiment, we get an output of images shown here. So as we apply load, you can see it begins to darken in these lines, which is the damage we're looking for. Some observations are that we're working with very large strains. We're also experiencing this darkening effect of the laminate as the load is applied. And critically, the cracks that we're looking for, these darkened lines here, are also very similar to stitching effects in the laminate. And we must be able to distinguish between these two when we want to actually characterize the damage. So, getting into the actual method itself now of matrix cracks. The first part we do is on images we acquire, define a region of interest. All the subsequent images, we then find the same region of interest in the pictures by computer methods. We crop to this region of interest, and then we deform the images so they have a consistent size across the whole image series. After this, we can go into the actual finding difference between, or finding damage that occurs in an image. So here we have two images in sequence from which we get this output here, and the black lines in this image are the cracks we're trying to detect. All other methods in the literature use what is called absolute difference, where you compare the reference image to a later stage, and this is done so you have always a clear image of what the total damage is. But this cannot be done here, because when we try, we get an enormous amount of noise in the images, and we cannot really distinguish what is damage, what is stitching, what is anything really in these pictures. So that is why we do sequential difference. Then we get to the last bit of the noise. We use a morphological filtering to remove this noise. So here is a raw output. We have what is a crack here in the middle, but we also have small lines which are caused by stitching fibers or other sources of noise. With the morphological filter, we're left with just this line from the crack, and we can then actually go into detection of where the cracks are. So for a full image here, we calculate the mean pixel intensity across the image, and with a peak finding algorithm, we then detect the cracks. For each image, we then must establish this absolute damage state again that we lost by using sequential images. And this is done by mapping to a fuller image. So here we have our new crack growth in the green, and we have the existing crack growth we found in previous images in the red here. With this method, we must now test that it actually works as intended. As part of that effort, we've developed a completely synthetic image generator. This is based on the experiments we performed. So we have the experimental results here, and we have the synthetic results here. And what this allows us to do is completely on the computer define cracks in a laminate where we can choose any orientation, any length, and any amount of cracks. And we can also simulate the noise that we see in experiments. So these are the stitches, darkening, deformation, and burring effects of the cracks. And this allows us to really control, and in our verification studies, where is the problems with noise and what is the most serious part. We then use it for verification, where we take a very difficult case and simulate. So we're working with poor crack definition, interfering crack orientation, so overlapping cracks, large strains, and darkening of the laminate. This is passed through matrix cracks, and we are left with the result of here the length of cracks in total detected and defined. And these two curves follow each other very nicely, which is what we want to see. The maximum error that we find is here in the beginning of 6%. We also do validation, so testing it against real experiments, real life. This is done via microscopy of our specimens after the test. So we take our specimens and with a microscope photograph the side of the specimen, so not the side we used for the front we used for matrix cracks, but the other side. And we get images such as this. The task is now to count the cracks, but as mentioned earlier, this is a subjective measure. So we need to define what is actually a crack here. What we did was take the cracks that we expect, which are working normal to the plane of or direction of tension, marked here in red, but we also have cracks that are occurring out of this plane, marked here in green. These are also counted as cracks, but as new cracks. The crack densities we calculate based on these results, shown here, where we have a slightly higher value for the manual result. This can be explained by how we define cracks. With the manual counting, we have to assume that the cracks have full length, so they cross the entirety of the specimen. Whereas with matrix cracks, we account for that they don't grow the entire way and can have partial length. Therefore, it's also, it makes sense that we have a slight difference here, that matrix cracks is a little bit lower. In conclusion, we've shown that matrix cracking is difficult and labor intensive. We've developed our method, matrix cracks. It automates this crack tracking. It is at least as accurate as a skilled operator. And what's more is that it is very robust against noise that we found in experiments. And now we will apply it to a preform transition, which is the work covered in paper B. Much of the motivation we have been through already, but preform transitions and transverse preform transitions already exist in blades, and they are, of course, a potential weak spot. So we must prove the structural integrity of these preform transitions, and to do that, we must characterize the damage that we see. Structural integrity is, in our case, proven by comparing to the continuous laminate. So our assumption is that if we can prove that the transition is as strong as the continuous laminate next to the transition, then it should be upholding the structural integrity. So if we compare to the continuous laminate that we're seeing just beside the transition, we are working with biaxial materials, unidirectional materials, but there's also a preform transition interface in these. When we then compare it to how the transition actually looks, we have this quite more complex shape or geometry, where in the transition region, we have overlapping materials and ply drops terminations. And also a fact that must be noticed is that we have a little bit of additional biaxial thickness or thickness of the biaxial layers due to this overlapping. The load case we're considering is what is called ovalization of a blade. So when we have a full blade that is loaded in bending, the cross section is deformed. And what this does is that it causes tension across, or normal forces across the transverse preform transition as shown here. Getting into the experiments, the specimens that we're working with are these three. So we have a reference specimen, which is our nominal continuous laminate. Then we have our short transition specimens, which is sort of an aggressive design of how they can look. Then we have the long, which is a more relaxed. And the reason that we use these last two is that differences between them might indicate a weakness to manufacturing inaccuracies. Or if they're equal, then they seem to be robust. The results we get from testing, just the structural response we look at here. So the first thing we can see is that some damage occurs here at 200 Newton per millimeter of width of the specimen. What's more is that after this, the curve up here, we see that the transition laminates which are completely overlapping here, but support a slightly greater load compared to the reference specimen. The damage, of course, also reduces residual stiffness, as shown here with the stiffness. And what we see is that this point here is associated with a large decrease in the residual stiffness. Looking a little bit closer at the residual stiffness, we see that the reference specimen reaches their minimum very quickly. So this is the black curve here, whereas the short and long specimens have a more gradual reduction. This is actually a benefit because this more gradual decrease in residual stiffness is also an indication of failure, and so might provide a warning sign for the complete structure as the wind turbine blade. More is that the final stiffness is approximately equal, but overall the differences are quite small between these specimens. So this is already a good sign that things are not critical in the transverse preform transition. We'll also go in and look a little bit at the actual damage that we see. So the first failure that we can observe is happening here in the laminate. It occurs basically everywhere, we will see in a moment, but this is the damage. It is a matrix crack occurring here if it was hard to see. What we can see is that it is traversing most or all of the UD layers, unidirectional layers here in the middle. It is arrested by the biax layers, which means that it doesn't grow into the surrounding layers, meaning it is contained. What's more is that it doesn't appear to be affected by the preform transition, meaning that it doesn't kink or is arrested or grow in the interface of the transition. So this leads us to a hypothesis that matrix cracks are independent of the preform transition, which would be a good conclusion for our blade. One thing that must be considered for the further studies is that while matrix cracks do not necessarily cause failure of the global structure, this is because they can be contained by the surrounding layers, as we see here, and in all properly designed laminates, this should also be the case, that they are arrested by surrounding layers. But the issue is that these might initiate delaminations, so here, which can be a much more critical failure mechanism and leads to, again, global failure of the blade. So we must understand the density of these cracks to determine how many potential initiations of delamination do we have. How critical is this? The results we get from matrix crack density, we of course get from our method. And here we see the local crack density across a specimen. And some observation can be made from this. From this final state at the high loads, we see that the transition regions here in the middle seem to have lower crack densities. But you might have noticed that at the low loads, the reverse is true, where we saw crack density increasing for the transition specimens first. This is a little bit more obvious when we separate the crack density out into the region types. So here we're looking at the transition region for these curves, the crack density in the transition region. And for the high loads, this seems to be lower than the nominal regions, the continuous regions, which is what we want to see. However, for the low loads, it seems that the damage is occurring earlier and at higher rates. To understand what is going on, then we look at the location of these first cracks. So here we see a plot of the first 5 cracks observed on each specimen. And for the reference specimens, they seem to be distributed evenly. This is as expected. For the short specimens, we see that the first cracks appear primarily outside of the transverse or the transition region. For long specimens, they seem to be concentrated, and they seem to also occur in the transition region. We're particularly interested in this part here, which we will now look a little bit closer at by inspecting the laminate for flaws. So we will look at particularly in this point here. This study is done for the whole laminate, so we're not missing anything. But returning to the region here, if we zoom in, we get this image here in the microscope. We see a thickness reduction at the first crack here, so visualized as a little dimple in the total laminate thickness. What is more is that this is caused by a small gap between the UD layers here, so where they during manufacturing didn't completely meet. However, it is a very small defect of approximately 1 millimeter in length here. Our expectation is that a gap such as these are also occurring during manual layup. So putting down a fabric is very difficult. For a fabric that might be a half meter, full meter in width is very difficult to put down to millimeter precision, sub-millimeter precision. And what this means is that we have these defects in blades that are already spinning on turbines and they're not falling down. So we expect that these inaccuracies can exist without issue. So this is not so much of a problem for the preform transition. Summing up, we see that the structural response residual stiffness is similar. There's even a little bit of beneficial decrease or less severe decrease in residual stiffness for the transition. We had the hypothesis that matrix cracks are independent of the preform transition, but what we actually saw was that the crack density is lower in the preform transition regions. We also saw that the matrix cracks that appear first are caused by manufacturing inaccuracies rather than the preform geometry. What this means is that the transverse preform transition is at least as strong as the surrounding laminate, perhaps even stronger because of the overlapping biax layers. And finally, our conclusion is that the current blade design is still valid, and using the preform transition, preform manufacturing concept in general, is not going to lead to blade failure. So we now get into the prediction part of failure in laminates. The issue here is that we're now turning our attention to the actual preform transitions, where these are expected to be much more severe than the transverse preform transitions. The reason for this is that as part of the transition, we interrupt the continuous load-bearing fibers and thus introduce severe discontinuities, which might initiate delamination. And a particular critical thing that is a worry here is that a delamination might initiate in one discontinuity, but then grow as a zipper effect across the whole transition and thus fail very quickly the entire thickness of the laminate. To study these, we need models. Evaluating this, typically what we're interested in is the far field response. So how does this transition interact with the entire blade? The loads that are applied, can it sustain these? To figure this out, we must consider the full complexity of the transition, where we have multiple fiber layers, we have discontinuities, we have voids or matrix pockets in the laminate, we have ply drops, and a lot of potential delamination initiations. All of this complexity means that simple failure models are unsuited for this problem because of the complex geometry and a lot of damage initiations, which might again interact or are in fact expected to interact. To solve these models, we need finite element models, and these need to be finely discretized solid element models using cohesive elements to capture delamination damage. The issue here is, however, that these are time consuming, and therefore they are difficult to use in a design context because you cannot design a laminate and then have to wait a week, 2 weeks maybe before you see the results and then change your design. Our vision to approach these issues is to introduce surrogate models. So our idea specifically is to substitute the local nonlinearities, which are the damage, delamination cracks, by a surrogate model. And what a surrogate model is, basically, is that we take a very complex phenomena and substitute it by a more efficient and simpler to evaluate model. Our hope is then that the surrounding mesh, where we have only linear behavior in our finite element models, can be meshed less refined, which leads to coarser models, which are faster to evaluate, and then we have much more efficient evaluation of such a detail. Getting a little bit more into the specifics of how we want to approach this is that we define a fracture domain. This is defined as a solid with an intersecting cohesive interface, as shown here in the red. The core assumption that we're working on is what's called Saint-Venant's principle, where it can be stated as the difference between the effects of two different statically equivalent loads becomes very small at sufficiently large distances from the load. And what we take this to mean is that if we only consider the boundary response, then we don't expect it to be as severely nonlinear as what is happening close to the crack in here. And that means that we can take the boundary response alone and then approximate this, of course, by a surrogate. The benefit of this will be that we can reduce the model order by orders of magnitude, and thus simplifying our models and approaching this more efficient modeling paradigm. We have some requirements for this, however. Since this fracture domain is going to be part of a larger solid, we must be able to prescribe boundary conditions on the entire boundary. We are, however, also interested in reducing the complexity of the boundary, and we must keep a well-defined boundary condition even when we do this reduction in the degrees of freedom. So just as the example here is that we want to go from this example with 128 or 120 degrees of freedom down to this where we have 28. To do so, we've developed a constraint element, and this is based on a quadratic 8-node element, which we collapse into this single line 3-node element. And what this does is that once we tie such elements to the boundary, fix them to our model, we constrain the response that the boundary can do to expected shapes. So the shape function of this element is a quadratic shape. That means that the deformation or the results that we get on the boundary will always be contained to quadratic shapes. And also, with this reduction, we are left with a limited or reduced amount of degrees of freedom, since we only have to interact with these constrained elements, and therefore we get this desired reduction. However, before we get into surrogate modeling, there are some questions that we must answer, which is what the paper was concerned with. One is the fracture domain accurate with respect to this far-field response that we are interested in? Here, as an example, a model can be as a dumbbell cantilever beam, as shown here, where we have a crack growing as such. The far-field response in this case will be the crack opening and the associated reaction force. A second question that we must answer is that, or is the fracture domain suited for surrogate modeling at all? We'll start with the first question here. Is the fracture domain accurate with the far-field, with respect to the far-field response? To investigate this, we make first two finite element benchmarks. One is a finely discretized DCB, where we use the discretization that is sufficient for our cohesive interface elements, and then use this element length everywhere. The second benchmark is a coarse discretization, where we use only just enough elements to capture the bending of our cantilever beams accurately. And then we use a similar discretization of our cohesive interface. Our fracture domain model that we're then actually interested in is somewhere in between, where we have this mixed discretization. And what we hope to do is approach the accuracy of A, or the first model over here, but also approach the speed of the coarsely discretized model, such that we get the best of both worlds. If we look at the response of the far-field response at the boundary condition, the structural response is mostly well behaved for all three models. If we zoom in a little bit, However, we can see that the model that is coarsely discretized has significant difference from both the analytical solution, but also our two other models. This is, however, also expected because it is overly coarse and is thus not expected to be accurate. The two other models are smaller difference, and our all three models here, the analytical, are finely discretized, and our fracture domain models are basically in agreement. What we see is that the mean difference, average difference, is nearly equal for these two models. So they are almost on top of each other in the difference to the analytical here. The variance that we see for our fracture domain model is a little bit greater, but it is still a fairly small difference. And what we take this to mean is that the fracture domains are actually accurate to the far-field response. Returning to the second question, whether the fracture domain is suited for surrogate modeling, the way that we want to investigate this is when we extract a data set of the fracture domain boundary response, and then we investigate the complexity of this data set. The way that we do this is that we take our DCB model, we run it through a number of boundary conditions, and then for each fracture domain defined in this model, we extract all of the displacements, and then we compute the reaction forces required to put that displacement in equilibrium for a fracture domain. The output of this, here we see the displacement states, all of the displacement states captured for a fracture domain, and you might be able to see the fracture domain as the black degrees of freedom as the black dots in here. To investigate it, we use principal component analysis to determine the complexity here. And what we get from this study is we can see how much of the variance in the data is explained by the principal components. And getting right into the results, here we see the first three of the most important components, principal components found. And it is immediately obvious that some are more important than others. So for the first displacements, we see that one principal component explains almost all of the variance found in the data. And comparatively for the forces, two components explain almost all of the variance found in the data. We take this to mean that the data can be very reduced, and this is also beneficial for surrogate modeling because this means we do not need complex surrogate models to actually represent the response that we see in the data. So in conclusion here, axial transitions require expensive finite element simulation. This is not good for engineering designs, and it is something we want to improve. Our idea is these fracture domains, where we expect this implementation, and we see that delamination is captured accurately by the fracture domain. What is more is that we see that the response data of the boundary response is suited for surrogate modeling. That concludes the work in the papers, and I will just now conclude the overall project results. So we set out to be able to detect, characterize, and simulate damage occurring in preformed transitions such that we could avoid structural failure of blades. Under these topics, we developed a detection method, matrix cracks, which is robust and accurate. And the impact of this is a characterization tool for faster evaluation of material properties for use in industry. On the characterization, we saw that the transverse preformed transition can be readily used in structures. And the importance of this is that it enables faster manufacturing of large composite structures, or in general, serial production of laminates. And finally, for simulation, we looked at the fracture domains, which enable a surrogate simulation of delamination. And the importance here is that eventually we get, or with this, we get one step closer to using surrogate models and thus introducing industry to our high accuracy finite element models that can be implemented in the engineering design process. And all of this is important to enable the green transition towards greener energy, both in the concept of cheaper wind energy, but also in the automotive and aerospace industries, where we can approach more lightweight vehicles and thus also more fuel efficient vehicles. With that, I end my presentation. Thank you all so much for your attention.